Good morning, everyone. I'm Mengying Lei, a PhD student from McGill University, and I'd like to share our recent work about scalable spatiotemporally varying coefficient modeling with Bayesian kernelized tensor regression. So first, about the motivation of this work. A spatial regression model with locally varying coefficients can characterize the complex correlations between the dependent variable and the independent variables. So this type of model plays an important role in many research fields, such as the studies in geography, ecology, and economics. For example, if we have the crime locations in a city, we can build a spatial regression model to understand the factors behind the patterns of the crime. More specifically, we can discover what variables such as income or education can explain the crime locations. And based on this regression model, we can further predict future crime locations and even use it for decision making. For example, to choose where are suitable locations for police stations. And usually in a regression model, for this case, the crime locations, the output variable, are called dependent variables, and these explanatory variables, income, education, are called independent variables, and the relationships are usually captured by the beta coefficients, and there also has a residual part to denote the noise that cannot be explained by the model. So formally, we can represent a local spatial regression model as in this equation, in which here S is the index for spatial locations such as the longitude and the latitude. XS and beta S are length p covariates, are length p vectors denoting the covariates and regression coefficients at the corresponding location S respectively. And here the epsilon S is a white noise process with a precision parameter tau. Generally, there are two classical methods to do the spatial regression. The first is the Bayesian spatially varying coefficient model, the STVC model. The second is the geographically weighted regression, the GWR model. Specifically, the STVC model is a Bayesian hierarchical model in which the regression coefficients are modeled using Gaussian process. For example, for a connection of M observed locations, the STVC model assumes the vectorization of the coefficient matrix beta max follows the zero mean Gaussian process, and the covariance matrix is a Kronecker product of Ks and lambda. Here, beta max is a M by P coefficient matrix, Ks is a M by M spatial covariance matrix, and lambda is a P by P precision matrix for the covariance. So based on the Bayesian formulation of STVC, this model enables us to learn the kernel hyperparameters, and we can also explore the posterior distributions of the coefficients and also perform prediction with uncertainty measurements based on the sampling methods, Markov Monte Carlo, MCMC. And on the other hand, the geographically weighted regression model, the GWR model, is usually developed independently using a local weighted regression approach. And usually a bandwidth parameter is used to assign weights for different observations, with closer observations carrying larger weights. So the performance of the GWR model is highly sensitive to this bandwidth parameter. And in practice, this parameter is often needs to be pre-specified based on domain knowledge or tuned carefully through the cross-validation. So comparing these two methods, we can see that the STVC model can learn the kernel hyperparameters, which are critical to understand the spatial temporal processes. And the STVC also allows us to explore the posterior distributions for both the regression coefficients and the prediction results. So compared with GWR, the STVC have better property in such regression task. And we can naturally extend the spatial regression to spatial temporal regression, which further capture the temporally varying effects of covariates. For example, assume we have M by N panel response matrix Y, which is observed from a set of locations S over a set of time points T. then spatial temporal regression model can be formulated as in equation number 2. Here we use M and N to index the rows and the columns respectively, and where Mn is an element of the data matrix Y. And X and beta are the covariance vector and the coefficient vector at the corresponding location and time respectively. Accordingly, the GWR has been extended to GTWR, geographically and temporally weighted regression, which follows the same local weighted regression approach by introducing more parameters to quantify the spatial temporal weights. And for SVC, it is extended to STVC, spatial temporally varying coefficient model, by using a separable kernel structure. Specifically, if we put all the coefficient vectors into a very long vector, then this vector follows the Gaussian process with zero means, and the covariance matrix is the Kronecker product of KT, KS, and the lambda. Here, KT is an n by n correlation matrix for the time dimension. But this STVC model is hardly ever used in real-world problems, mainly because of the high computational cost in Gaussian process estimation. For example, for a fully observed matrix Y with the corresponding spatial temporal covariance, the time complexity in learning the Gaussian process hyperparameters in each MCMC iterations is proportional to the cubic of M times N times P. This could be prohibitive for recent real-world data sets. So to address this challenge, in this work, we provide an estimation strategy for the STVC model to deal with large-scale spatial temporal data, and we refer to our model as Bayesian Kernelized Tensor Regression. We first summarize the regression coefficients as a three-order tensor, B with a size of M by N by P, and the Mn mode 3 fiber, the Mn mode 3 tube fiber of this tensor B, it corresponds to the length P coefficient vector at a corresponding location and time. And based on this formulation, we use CP decomposition to model this coefficient tensor. And in order to further incorporate the spatial and temporal dependencies, we impose Gaussian process priors on the factor vectors decomposed from the tensor B. And so by doing this with a predefined tensor rank, the complexity in learning the kernel hyperparameters can be substantially reduced compared with the default STVC model. And we conduct numerical experiments on both synthetic data and real data sets. The results validate the performance of our proposed BKTR model. Next, I will briefly introduce the methodology of our model. Assume the script letter X is a M by N by P tensor, and we use it to denote the covariance information. Specifically, the Mn mode 3 fiber of X is a covariance vector at a corresponding location and time. And we use a lowercase letter y to denote the vectorization of the data matrix Y. So then the previous spatial temporal regression model can be rewritten in this equation. Here, the uppercase X3 and the B3 are the mode 3 unfoldings of the tensor X and B respectively. And in this equation, the first part denotes the covariance information, and we use the X hat to represent it in the following equations. And the second part denotes the coefficients. So if we assume the coefficient tensor B admits CP decomposition, then this equation becomes as follows. And here the UVW are the denote the decomposed factors of B. And if we further consider that the observation data contain missing values, we can write the generative model of BKTR. Here the omega denotes the observation indices, and the matrix O is a binary matrix indicating the locations of the observations. And by doing the CP decomposition, now the number of the parameters the number of the parameters is R times the summary of mn and p, which is largely reduced compared to m times n times p. And to encode the spatial and temporal correlations, we assume the spatial and temporal factors follow the Gaussian process. Specifically, for each column of U and V, we assume them follow a normal distribution with zero means, and the covariance matrices are denoted by Ks and Kt. And for the kernel hyperparameters of the Gaussian process kernel functions, we assume their log transformed values follow a non-informative normal distribution, since there does not exist any conjugates prior for the Gaussian process hyperparameters. And for the matrix W, factor matrix W, we assume each column follows a normal distribution with zero means, and the precision matrix is denoted by lambda W. And we further place a conjugate Wishart prior on its precision matrix. And for the model noise precision parameter tau, we assume it follows a conjugate gamma prior. We derive the corresponding posteriors for the model parameters and hyperparameters, and we develop a fully Bayesian sampling method to update these parameters and hyperparameters. Next, I will introduce the experiments part. So we first test the performance of our proposed BKTR on a small data set, in which the true coefficient tensor is generated following a separable covariance matrix. Specifically, we generate 30 locations and 30 time points, and 2 spatial temporal covariates. Here, the first frontal slice of the covariate tensor X is an m by n matrix of ones, which is used to accommodate the intercept of this regression model. So the set of the covariates dimension, the value of p equals 3 here. This table shows the performance with respect to the estimation of the tensor of the coefficient tensor. We compare our proposed BKTR with the original STVC model. We can see that the BKTR provides similar estimation accuracy compared with STVC, but in the meantime, our model, the computing time of our model is dramatically reduced. This means that this kernelized decomposition can successfully approximate the coefficient tensor. And we also compare the BKTR with BTR, Bayesian Tensor Regression, which does not use the Gaussian process priors on the factors. We can see that the BTR cannot provide very good results. This emphasizes the importance of Gaussian process for characterizing the spatial and temporal correlations in such tasks. And to evaluate our model on dealing with large data sets, we further generate a relatively larger data with 300 locations and 100 time points, and 4 spatial temporal covariates, except the data size. The other settings are the same as the first simulation, and we randomly choose 50% of the data as missing values. Here is the results. The figure B shows 2 examples of the estimated coefficients. We plot the mean estimation with 95% correctable interval. We can see that the BKTR can effectively reconstruct the true coefficients and provide a valid correctable interval. The panel C, figure C shows the effect of the tensor rank. You can see that with a larger rank, the model performs better, but the accuracy gain becomes marginal when the tensor rank is larger than 30, which means that our Bayesian treatment provides a flexible solution in terms of both model estimation and parameter inference. And we also perform our BKTR model on a large-scale back-sharing trip data connected from BigC, a back-sharing service in Montreal. BigC operates more than 600 stations, and the yearly service time is from April to November. So we connect the number of daily departure trips from for each station over around 580 stations. And following the previous studies for the BigC data, we considered 13 spatial covariates and 5 temporal covariates. When further consider the intercept part, the value of P is equal to 19.
Mengying, I just want to notify you that you have 2 minutes left, and unfortunately there won't be any question time but we want to hear your presentation, so I think it's better that you finish, but I think you have 1 minute left until the next participant.
Okay. So here is the this figure shows the temporal plots of coefficients, and we can clearly see the strengths and temporal trends of each coefficient. And I also show the spatial maps of coefficients. We can also get a consistent result. So this is finally a brief summary. So in this work, we propose an effective solution to dealing with large-scale local spatial temporal regression analysis. And compared to the previous studies on tensor regressions, our proposed model integrates the Gaussian process priors to characterize the spatial and temporal dependencies. And this kernelized decomposition can largely reduce the number of parameters. So finally, I would like to thank Lijun for funding this research, and thank you. That's all for my presentation.